And I'm going to hand over to James and team, who leads our OpenStack architecture at Canonical, to talk through LXD and KVM and why we think this is so exciting. James?
Okay, thanks. Right, okay. So just a quick introduction as to who I am and who my colleague Ryan is. So my name's James Page. I'm technical architect of the Ubuntu OpenStack team. I've been with Canonical for about 4.5 years now, but I've been deploying and working with open source technologies for about 15 years in fairly large enterprises before Canonical. I lead the team who's responsible for all of the packaging that you use for Ubuntu OpenStack and for all of the charms that we deliver for deploying OpenStack using our Juju service orchestration tool. I'll hand over to Ryan to introduce himself.
Hi, I'm Ryan Harper. I've been with Canonical about 1.5 years on the Ubuntu server team, technical lead there. And prior to that, was at IBM's Linux Technology Center, and I've been working on virtualization, open source virtualization for about 12 years there.
Okay, so before we dig into some benchmarking figures that Ryan's going to run us through, I'm going to take you through our products and around containerization and the work we've done in the last 6 months since Paris when we announced LXD, our new Hypervisor product. So what's LXD? LXD is, as I said, it's our Hypervisor. It's designed to run full machine containers. So we're differentiating from things like Docker and Rocket, which are very much around running process-based containers. It's a full machine container, and I'll dig into that in a little bit more detail. We're very much targeting getting close or at bare metal performance for those containers, so as little as possible between your workload and the underlying hardware you're running on. That allows us to achieve some very high density figures for the number of containers you can run on a certain specification of hardware due to a very, very small overhead for each container. So let's dig into what that machine container terminology means compared to process containers in a bit more detail. So in the slide I've just popped up, we've got a host machine, either bare metal or KVM. We'll talk bare metal for purposes of this talk, and we've got a couple of containers deployed on it. And each of those containers feels very much like a full system. So they're running a standard, trusty or vivid Linux image. You've got init running, you've got cron, syslog, you can SSH to it. It feels very much like a full virtual machine that you would get under KVM. And that's the parity we're looking to achieve with LXD. We're not trying to compete with Docker. And in fact, it can include Docker within that. So it's perfectly feasible to run a number of process containers within a machine container and have a level of nested containerization to give you more flexibility if you want to do that as well. Okay, so kind of digging into LXD features in a bit more detail. Some of you may have seen my colleague Tycho's Doom live migration demo from Paris, where he live migrated a running Doom demo between machines. And we've been doing quite a lot of work on that in the last 6 months to leverage CREU, the checkpoint restore and user space toolset, to perform smooth, fast, and reliable live migrations. There's still a little bit of work to go on that, which I'll touch on later in the talk. But if you haven't seen that demo, please go down to our booth in the expo hall where that's running all the time, and you can see the fantastic Doom live migration running. Got a real strong focus on security. So by leveraging a number of security technologies, we're able to deliver unprivileged containers. So these are containers where all of the processes within that container are running not as root. And this is very important in terms of the security around our container architecture. So by doing that, we're able to provide an increased level of assurance that if, God forbid, a container breakout did happen, then that's as an unprivileged user on the host. So the impact of such a possibility is much reduced. But to kind of beef up around that, we're leveraging a number of well-known technologies. AppArmor in Ubuntu is very much used to enforce security about what the processes within a running container can do on the host OS. And we're working with most of the major instruction set owners in terms of enabling hardware assist for container security as well. That's not something that's generally available, but as and when it becomes more consumable, that's something that we'll be delivering as part of LXD. Okay, so touching on another couple of things, networking and storage. So The approach we're taking with LXD is basically if it can be presented on the host, we can plug it in a container. So we're not doing any heavy lifting in terms of integrating with something like Open vSwitch or any SDNs or specific storage solutions. We're taking the approach that if you can present it on the host OS, it can then be consumed within the containers that you're running on top of that OS. So we're avoiding the heavy lift in LXD. Fortunately, we have quite a well-known cloud product, which does a lot of that for us. So this fits nicely alongside something like OpenStack to provide the networking and storage components into a container architecture. Which leads me quite neatly on to the other project we've been working on in the last 6 months, which is our Nova Compute LXD driver. So this is a drop-in replacement driver for, say, the libvirt KVM driver that allows you to manage LXD containers in an OpenStack cloud in a very similar way to KVM instances. We've got a technical preview release out with our Ubuntu 15.04, which came out last month. And in that, we've got some support for fast rootfs cloning. We run everything by default as unprivileged containers to assure a level of security. We've got a base level of neutron integration with the ML2 OVS reference implementation. We're fully integrated with Glance, so you can store your LXD root tables in Glance and use those across your cloud just in the same way as you would do for libvirt KVM. And we've enabled support for LXD in our Juju TARM for Nova Compute. And it literally is just a single config option to switch between KVM and LXD as the two options. And that allows you to deploy an entire OpenStack cloud using bare LXD containers underneath the hood. Okay, so I'm going to hand you over to Ryan now. He's going to walk you through some of the detail of containers and some of the benchmarking we've been doing.
Thanks, James. So what is in the way of the workload? Let's get started on that. So what we have here is kind of a layered picture showing how we're stacking things together. We've got our physical machine. You boot your Ubuntu Linux kernel, put Ubuntu Linux on top of it. And on the left, if we start up a KVM instance, virtual machines are meant to look very much like bare metal. And so they have all the same things that your bare metal system had. It has a BIOS. It has a bootloader. It's going to load its kernel. And it's going to run through its operating system, user space, come up. And then you get to the point where you can run your workload. There's lots of extra stuff that happens to simulate that machine. In the kernel, it's still probing virtual devices, emulated devices, doing all these things. And that has to happen because it wants to behave like a real machine. In LXD, we don't have any of that. The containers run as processes directly on the host as processes. We do go straight to init, but we don't have a BIOS. We don't have device drivers or things like that. So that makes things a lot thinner. So if your application's running in the virtual machine, a couple things have to happen before it starts to run. When your application is running, the virtual processor in the KVM needs to schedule your workload process. The host itself needs to schedule the virtual processor to run as well. And so a lot of this introduces just extra time and latency and overhead to actually running what you need to get done. So there's a couple of interesting things that happen on large SMP guests as well as overcommitted hosts. The host operating system, the Linux kernel, has to help provide some switching between all these different virtual processes. And in the pure virtual machine world, we talk about a problem called lock holder preemption, where your guest OS is holding a lock while your other parts of your workload may need to do some work, but it's not actually being scheduled by the host. And this is actually a big deal. The silicon vendors have introduced features to detect this particular situation and tell the hypervisor, by the way, you're not going to get any further with this particular one. Why don't you schedule something else? So for LXD, this is not a problem. And without having lots of extra layers of resources being occupied, that leaves LXD to do things quite well. Let's look at that. So density, just from a memory footprint perspective, our we don't have all those extra stacks in that layer in that picture. So we can put a lot more of these machine containers on the same system. And this means that we can do more with the hardware that you have. You can pack more into there. And this increases our utilization. So we intuitively kind of knew this, right? Containers aren't as heavyweight as the virtual machines, but we really wanted to kind of take some time and say, well, let's put some numbers next to this. And so to get a real number, we took an Intel server, 4-core, 16 gigs, pretty stock setup, and we set up Ubuntu Linux on it, and we decided we'll launch KVM instances with Ubuntu server image, and we'll do this until the hypervisor is out of resources. In this case, the one that we're most constrained with is RAM. So we'll do that, boot up as many as we can until we can't anymore, record that, and then we'll do the same thing with LXD, using the exact same image, but using the LXD virtualization technology. So let's take a look at that. On the left, we launched about 36 containers. This is another run where we got a few more. And that was what we expected. These were 12 megabyte virtual machines. They boot up, and KSM's active and doing some work to deduplicate pages. But at some point, just all that overhead that happens. These are all full guest OSs with that big stack. Remember that big stack that's got everything in there? It just takes up space. So we reran with LXD's basically exact same experiment, but with containers where each machine container just has dramatically less memory footprint from each one. And so with that, we had a dramatic number here, over 600 of the same Ubuntu images are running on this same server. So that was extremely impressive. Now that we saw this and we said, this is really good, but let's take this and put it in the context of the cloud. So if I can take a single server and stack very, very, very many LXD machine containers, and then for the cloud, that means we should have some significant density. So we built a 10-node OpenStack Kilo cloud on Intel servers, a little bit bigger. I think there were six cores and 48 gigs of RAM on them. And then we ran in a converged architecture, so a lot of the infrastructure was housed on some nodes. And that gave us about 6 compute nodes for us to run this experiment. And we did it with KVM, and then we did it with LXD, the Nova NC LXD driver. So let's look at where we got. Now, some explanation for the graphs. These are ganglia monitoring graphs that we grabbed while we were running a boot test. So we just kick off a Nova instance and keep it going, and just keep it going until the cloud kind of falls apart. The blue in the charts represents committed memory. So that is memory that's been allocated from the host perspective, it's allocated to running applications and processes. The green represents cached memory, buffer cache, page cache, things that Linux does to speed things up for read and write operations and things like that. There's one more color, purple, on the lower right on KVM indicates swap. So that's when we've started committing memory that's not being actively used and touched into swap. And things get noticeably slower when we get in there. So on the KVM side, we hit about around 1,000 instances or so is when we kind of hit the red line in there, and we started getting into swap. And it continued to swap, and we committed another, I think it's another 48 gigs or so above to get that last remain. And we started swapping, we said, all right, we'll kill it now. We can't get any further with that. And we reran with LXD. And as we were getting up, I think it was around, it was about maybe 1,200, 1,300 instances, we were steadily increasing, and it was good to see this memory footprint where we have tons of greens, just as we have a huge amount of headroom where we can continue making containers. And we flatlined for a little bit. You may be able to see under the 1,800, there's a bit of a flat line, and the benchmark came back and said, I can't allocate. I've got a resource problem. And I said, well, I'm looking at the chart here, and it's like, there's plenty of RAM left. So I was talking with James, and I said, James, what's going on here with this flat line? What was happening?
Yeah, so it turned out we'd hit the scheduler limit. So the scheduler was saying, actually, the compute host has got no more memory. So the default RAM and memory allocation limits that we ran the test with weren't sufficient to deal with the density of containers that we could get on each compute host. So we actually just twiddled those knobs, increased the overcommit a lot so that we didn't hit it again, and the cloud started creating instances again. So it just shows that the difference between, we didn't hit that on the KVM test. I think we probably would have ceilinged at about 1,400 instances with the configuration we were running. But we hit that relatively rapidly with the container test, and we just had to tweak that up and allow a higher level of overcommit on each host.
So once we fixed the overcommit ratios and set them rather high, 1,000 or something, just keep on going, it continued to climb on the web. We ended up cutting off about 1,800 instances or so as the infrastructure, converged infrastructure, was just making the spawning really slow. And so we said, I think we've covered, and the picture kind of shows exactly what we wanted to show in terms of how frugal LXD is with memory resources. Let's see here. So another feature, something that matters, is startup time for developers, right? If you're iterating on a project or a workload or whatever, you can go through your workflow faster and faster if you're not waiting on things to happen. I mean, how many people have rebooted a physical machine and you're waiting for the 5 minutes for the enterprise firmware to finish probing devices just to get to the bootloader and run? And virtual machines are certainly faster, but LXD, remember that picture that we drew? We don't have that virtual BIOS. We don't have another bootloader, another kernel to load and run. We're right into the workload immediately. And so this means startup time is dramatically different. So LXD launch Ubuntu VM1, 1.5 seconds, and we're in, we're running, right? All the processes that you saw earlier are already going. You can SSH in. That's there. For the same KVM instance, we've got to go through all those things in that stack to get all the way up and finish its init, and then we're in there. So that makes a big impact for workflows. And so if you recall the first density test that we did, we took some, and you look at this startup time, we went back and looked at the time it took to do the density run. So when we launched the 36 or so of the KVM instances, we kept how long did it take for us to actually get that far. And then for the much higher, over 500 for the LXD containers, we looked at the time it took to get there. So same server, launched our 37 in 943 seconds, and then when we launched, it was amazing to see that we had launched more than 14 times the number of instances, but in less time, about 20% less time than KVM. So startup time matters, and the density matters, and that really combines for some powerful technology. I wanted to talk about another LXD feature when you think about that stack and how thin it is and what this enables. Latency. So latency is important for many workloads. So telcos are very much interested in reducing the amount of time it takes to respond for message passaging and things like that. Even in an OpenStack cluster where we're sending messages all across the bus, latency can make a tremendous impact on the speed of your cloud and how quickly you can react. So we did a benchmark here. So we looked up the 0MQ as a latency benchmark, and so we set this up. The remote latency setup here is 2 KVM on the top. We have 2 KVM VMs running Ubuntu. They're on the same host, on the same software bridge. And the test itself sends 1 byte packets, 1 million of them, and then averages the latency across at the time it took for each one of those as well. And in this case, one of the KVM guests, when the test starts, needs to send the packet. This is going to go through, the networking layer of our IONet. It's going to go down into the host, take the packet, goes to the bridge. It's on the bridge, comes back up into the other guest. It has to wake up and be scheduled and picked and then sent into the user space, and then you get a response. And so that can take a long time. Exact same setup with LXD, 2 container machines on a shared bridge running the exact same test, and we're over 50% less latent. And that's just, there's not as much in that stack that we have to go through, which means that your applications can communicate at significantly faster. The other test here, the local latency, takes the software path, or the networking part of the path. It's just the application talking to itself in 2 threads. And it was interesting to see the local latency on the bottom looks to me scheduling latency, right? We have two threads inside your virtual machine that need to be scheduled and context switched between. And we see a lot of the context switch overhead that you'll get in a virtual machine when we have to do VM exits, or you've got 2 schedulers and you've got to make sure that it happens quite right. In LXD containers, we don't have that extra layer and an extra kernel or extra scheduler. It's just the same processes on the host. And so we saw the same 50+% latency improvement on there. So before I hand it back, just wanted to cover some of these key benefits, right? So you think about that picture about how much we're taking out, but still giving you a full machine container and delivers these key capabilities, right? Density, right? We use less memory per system than you will with a KVM machine. That means you can stack more things together. Startup time, so your workflow, how quickly you can run through things, how you get through these processes has a significant impact on workflows. And finally, latency, right? These, for folks who are interested in high-speed workloads that require very quick response times, getting all that stuff out of the way of your workload means that you'll be able to get more of what you need done faster.
Okay, thanks, Ryan. So, as I detailed below, we've got a technical preview release out with our Ubuntu 15.04 release. So if you want to try it now, you can go and try it on 15.04. We're obviously not recommending this for production use yet. We've got a number of features that we want to work on and implement before we're recommending that people start using this stuff in production. And our target there is really around our 16.04 LTS. So this time next year, we'll have our successor to Trusty out for 16.04 in April. And we're aiming for a rock-solid container story with OpenStack at that point in time. So test now, give us feedback, tell us what's rubbish, what's good, and we'll definitely work on the results of that feedback. But in terms of what we generally got on the roadmap, we have an integrated roadmap between the LXD team and the guys writing the Nova Compute LXD driver. And we've got a few things that we're targeting over the next 12 months. So full block device support to allow better integration is top of the list right now. We're not able to directly present a block device into a LXD container right now. So we can't, for example, provision a Ceph RBD volume and then map that into a LXD container right now. But that's something that we feel for kind of parity with KVM and libvirt, that's something we absolutely need. So that machine container experience feels the same for LXD and for KVM and allows a much more comparative feel to the solution. So that's a high target for us. Broader Neutron SDN support as part of our work in the OpenStack Interop Lab. We're working with a number of SDN partners, all who have expressed interest in LXD and helping us enable their particular SDN in Neutron to work with LXD containers. So I've got a series of work there to enable things like Contrail, stuff like that. Broader image format support. So LXD is currently constrained to using a root table format, which if you use a cloud regularly is not what you use. You're typically using a raw image or a QCOW or something like that. LXD itself is going to be growing support to support a wider range of formats. So we'll get that natively via LXD. So if you're using LXD standalone or as part of a cloud, you'll be able to use the standard QKR2 image that you're familiar with using with Ubuntu on KVM, but with LXD containers as well. We alluded to this during the performance benchmarks we talked about, especially around density and the fact that we hit the scheduler limits pretty quickly with containers. So kind of resource management and usage reporting back into Nova is, again, another key focus. So figuring out how we represent the lighter footprint of a container back into Nova and how we manage that more effectively. So how we limit a container to, say, only being able to consume a couple of cores or a certain percentage of the memory of the host. They're all features that are coming in LXD to be able to constrain containers and have a container know it's only got a certain footprint. It's only got 2 cores, it's only got half a gig of memory. That's a feature that isn't in LXD in the compute driver right now, but that's something that's coming over the next 2 releases. And full live migration support. So we can do live migration now. There are some bits that don't get live migrated, mainly the security bits. So Tycho's been working on that to make sure that when you live migrate a container, the security around it also gets live migrated as well. So that's the broad roadmap we got between now and 1604. I hope you can see how we've come in the last 6 months to have an initial product for our 1504 release and where we're going in the next 12 months. It's pretty exciting. I think it's a very compelling story, especially when you start looking at the latency figures that Ryan highlighted, and how much closer you can get a workload, whether that's a virtual network appliance or a big data workload. You can get it right down next to the bare metal and get that bare metal performance, but still have the usability of a cloud like OpenStack. Okay, so
We're about out of time.
I think we have to wrap up now. If there's any more questions,
Yes,
then we'll
feel
just
free
be
to
outside
come
for
up.
the break. So.